In his book, The Starry Messenger, Galileo is able to measure the height of the mountains on the moon. How is he able to do that? This is quite an astounding feat for someone especially who has never gone to the moon and who is the first to in fact have discovered that there are mountains on the moon. So in this lecture, what I want to do is talk about page 240 in A Student's Guide to the Grade Physics Texts, Volume 1, wherein Galileo in his book, The Starry Messenger, describes his technique. So I'm going to draw a picture that will help illustrate this. So suppose, for the moment, that we draw a picture of the moon. The moon is right here. And I want you to imagine you're outside of the solar system, kind of looking down at the solar system. Over here, you have the sun. These are not to scale, of course. What I'm doing here is I'm merely drawing them for the sake of showing the configuration of these three objects: the moon, the sun, and the Earth. If this is the configuration of them, and let's suppose that you are standing here on the Earth and you are looking up at the moon when the sun is over here. If that's the case, then you will see that this side of the moon would be illuminated, and this side of the moon over here would be in darkness because it's on the opposite side of the moon, the opposite side compared to the sun. Okay? Now, what would this situation look like as viewed from standing on the Earth? So this is kind of a view from far away. And maybe I'll say a side view from far away. The question is, what does this look like from standing up on the Earth? Well, I'm going to draw a picture of the moon. This will be a little bit more of a larger picture of the moon. Moon as viewed from Earth itself. So this is, if you were standing here looking up at the moon, what would you see? Well, you would see half of the moon being bright and half of the moon being dark. So this would be the dark part of the moon, and this would be the illuminated part of the moon where the sun is shining on it. Okay, and here is the thing that Galileo points out. He says, if you do this, occasionally you will see a little bright spot in the dark region of the moon. So a bright spot can be seen in the dark half of the moon. Why would there be a bright spot in the dark half of the moon? Well, this must be, he says, this is the peak of a mountain. This is the peak of a mountain. Why is it illuminated? Well, if the sunlight is coming from over here, this is where the sunlight is coming from, it would bathe this side, the right side of the moon, in light, but only if that mountain was tall enough to stick up high enough could the peak of that mountain be illuminated, right? And of course, depending on how high that mountain is, it will be more easily or less easily illuminated. And there's going to be a relationship between the distance of that bright spot from the center point of the moon, that we'll call that distance d. That's the distance from the peak of the mountain, where you see this bright spot, to the diameter drawn on the moon that separates the bright from the dark half of the moon. And as you might imagine, the taller the mountain is, the farther it can be from that diameter and still be illuminated. So how do we figure out the height of that mountain? Well, I'm going to write down some numbers that Galileo is aware of. He knows that the diameter of the moon, he says, is just about 2,000 miles. He says Italian miles. Of course, this is in the early 1600s. There's not a a universal, internationally adopted measure of miles. So you'll read there are Italian miles and German miles and so on. He's using Italian miles. So he knows the diameter of the moon is about 2,000 miles. You might wonder how he gets that, and we could, of course, go back and talk about that. But let's just take that for granted. The diameter of the moon is about 2,000 miles, which means the radius of the moon is right around 1,000 miles. And furthermore, he notices that this distance d, he says, is about 1/10 of the radius of the moon. So if you kind of compare how far this bright spot is away from the diameter line to the entire radius of the moon, it's about 1/10 of that size. In other words, d is about, he says, 100 miles. So this peak of this mountain is 100 miles away from this line separating the bright and the dark regions. Okay, now this is going to be enough information to figure out exactly how tall that mountain is. So what I'm going to do is I'm going to now draw another picture that is a view of the moon. So let's look again at a side view of the moon. This is going to look like similar to the one above, but it's going to be from the side. Okay, so here is the moon. And let's say this is the middle of the moon. This is point E. This is going to be similar to the diagram that he draws on page 240, figure 18.8. I'm going to draw it upside down though. And this would be the radius of the moon going out here to point C. And this line right here is going to go to point A. That is the location of this mountain. And the mountain is sitting up right there. And the height of the mountain is the length AD. And then what I'm going to do is I'm going to tell you, why don't I make this orange and this orange right here? And then I'm going to draw a line from the tip of that mountain that is illuminated by the sunlight that goes straight past that point C. It's supposed to be touching that point C over to the location of the sun. So these are the sunbeams coming in this direction that are illuminating this half of the moon. Right here, and of course the other half is dark. This is where the sun is located. And now what we're going to do is we're going to use the properties of that triangle to determine how high that mountain is. Okay, so specifically we're going to use the Pythagorean theorem. We've come across the Pythagoreans a number of times in this class. We're actually going to use the mathematical formula that's named after them right now. Remember, for a triangle, the sum of the squares of the sides, if it's a right triangle, the sum of the squares of the sides is equal to the square of the hypotenuse. So if we look at that triangle I've drawn there, the line segment CE, if we take that and we square it, plus the line segment CD and we square that, that should be equal to the hypotenuse DE squared. That would be the Pythagorean theorem. Now, note that CE, that is just the radius of the moon. So that is going to be 1,000 miles. I won't write miles, I'll just write 1,000 squared. What about CD? Well, that's the distance from that halfway point, the line between where it's illuminated and unilluminated, over to the bright spot where the mountain is seen. And he says that is 100 miles. So I'll put 100 right here, squared, and that has to equal this entire hypotenuse, which is the sum of the radius of the moon, AE, plus the height of the mountain, AD. So I'm going to write this to be the radius, AE, plus the height of the mountain, AD. And we'll take that, and that is squared. Okay? Now, notice that we can take 1,000 squared, we get 1,000,000, and 100 squared is 10,000. So here on the left-hand side, we have 1,010,000. And that is going to be this quantity AE plus the quantity AD, all squared, right? Well, we can take the square root of both sides. That's what I'll do right here. And when we do that, we get about 1,004, or about 1,004 to 1,005. I'm going to write 1,005, and that would be then the sum of AE plus AD. Now, why is this relevant? Well, because we know that AE, that is the radius of the moon, is 1,000 miles. So if we take that 1,000 miles and you subtract it off both sides, you get 5 on this side, and you get AD on that side. And that is precisely the way that Galileo was able to measure the line segment AD, and that is the height of the mountain. In other words, that mountain is about 5 miles tall.